Let's talk about the equivalence principle in general relativity. Often we use two elevators. One elevator is accelerating a equals g, and the other elevator is standing on the surface of the Earth. Obviously, a g field directed downwards. And then we send out light. That's the yellow line here. And also here. And then, oh my God, there is a difference, right? Delta c half plus delta c half. So that distance is delta c, but here is only delta c half. So that is a contradiction then, a paradox. The equivalence principle is wrong. But it is not wrong, because one delta c half here, that is actually coming from the equivalence principle. And the second delta c half is coming as a curved space contribution. Here is a metric in general relativity for a uniform weak G field. You see there is something special going on here. And in the accelerator elevator you have the Rindler metric, but there is nothing special going on with the spatial coordinates here. It's a flat space. So that difference gives one delta c half, and the equivalence principle gives the other one. So there is no contradiction. The equivalence principle is working just fine. And in another way of solving this so-called paradox is to instead relate the delta c half here, instead of the ceiling, relate it to the geodesic, the black line here. And then it's delta c half, and there is no contradiction at all. So then it's minus g relative to the black line, and it's minus g here. So it depends on how you compare things, but there's nothing wrong with the equivalence principle. Thank you very much.